Welcome to Cosmos Gang. I'm your host Cosmos. Today we'll be doing part 2 of Electric Charges and Fields, Class 12. Today's class will try to discuss about Coulomb's law. We have learned that when two charges are placed near to one another, they will experience a force either attractive or repulsive. Now, in this case, when we place two like charges near one another, we'll see a force of repulsion between them. Let's take an example here. I rub a cotton with a pen and a plastic rod. Both the pen and the plastic rod becomes negatively charged. You see the force of repulsion between them. Similarly, when I rub a pen and I place it near to some pieces of paper, in this case, the pen becomes negatively charged and the paper acts as positive charge. So they will be attracting one another. So Coulomb's law tells us how to find the value or magnitude of the force between these two charges, be it repulsion or be it attraction, to find the value of this force. Now, we'll discuss about Coulomb's law, how to find it. Now, as seen in the two examples, let's consider a charge here, Q1, and another charge, Q2, whatever charges, it may be positive or negative. Let's say these two are separated by a distance of r, then there will be a force between these two charges, either attractive or repulsive. According to Coulomb's law, he says that the force between these two charges will be directly proportional to the magnitude of the product of these two charges. Another thing is that force of attraction or repulsion will be inversely proportional to the square of the distance between the two charges. Now let's try to put that in words. So it states that the force of attraction or repulsion between two charges separated by a distance is, point number one, directly proportional to the magnitude of the product of the charges. That is, I can say that force is directly proportional to magnitude of the product of charges. Well, number two, inversely proportional to square of the distance of the line joining the two charges. That is, I can write F proportional to R squared. Now, let's try to put Coulomb's law in mathematical expression. Consider two charges Q1 and Q2 separated by a distance R. So, consider two charges Q1 and Q2 separated by a distance R. We know from Coulomb's law that our force is going to be directly proportional to the magnitude of the product of the charges, and our force is also proportional to inverse of the distance square. Make this equation 1, make this equation 2. Now we'll combine these two equations to get the final equation. While combining these two equations, similar terms are written once, whereas different terms are written once in their position. That means either in numerator or denominator. So combining 1 and 2, I get F proportional to Q1, Q2 divided by R squared. Now we know that whenever we change this proportional symbol into equal, a constant usually comes, and that constant is called as proportionality constant. Therefore, F equals K. K is going to be our proportionality constant, Q1, Q2 divided by R squared, where K is proportionality constant and its value K is going to be equal to 1 by 4 pi epsilon naught, which is equal to 9 into 10 to the power 9 Newton meter square Coulomb inverse square. So therefore, the above equation becomes, in place of K, I can write 1 by 4 pi epsilon naught, 1 divided by 4 pi epsilon naught, Q1, Q2 divided by R squared. So this gives us the magnitude of the force acting between two charges. Now, from Coulomb's law, mathematical expression, we find that the magnitude of force between two charges F equals 1 by 4 pi epsilon naught, magnitude of the product of the charges, 2, square of the distance between the two charges. Now, what is the meaning of this epsilon naught? We call epsilon naught as absolute permittivity in free space. In general term, free space means in vacuum or in air. So free space is generally taken as in vacuum or in air. Now, the value of epsilon naught, the value of epsilon naught is equal to 8.85 into 10 to the power minus 12 Coulomb square Newton inverse meter inverse square. The value of epsilon naught is equal to 8.85 into 10 to the power minus 12 Coulomb square Newton inverse meter inverse square. What is the meaning of epsilon naught? What is its general meaning? When I throw this pen in air, it has the ability to penetrate through air freely. Now, whatever force try to pass through or charge forces pass through the air or vacuum medium, it has the ability to pass through it freely. Now, that ability of the force of charge to pass through air or vacuum medium freely, that ability is called as absolute permittivity in free space, and we denote that with epsilon naught. So, the ability of the force of charge to pass or penetrate through free space, that is air or vacuum, freely is called as absolute permittivity. Now, this is the general meaning of absolute permittivity in free space. We have learned the above two topics. Now, let's try to test ourselves, try to answer this question. We'll try to apply the mathematical expression of Coulomb's law in this question together. The question states, two identical charges repel each other with a force of 45 Newton when placed in free space at a distance of 20 centimeters. Find the magnitude of each charges. To begin with, let us write all the given things here. I know my force is given to be 45 newtons. My distance is denoted by r, so r equals 20 centimeter. Centimeter is not in SI unit, so I'll convert it into SI unit, that is in meter. Now I get my r to be 0.2 meter. From the question, I find that the charges are identical, that means they are equal. So my Q1 and my Q2 are equal. Since they are equal, let's say it is equal to Q, and we want to find this Q. Now, using Coulomb's law, F equals 1 by 4 pi epsilon naught, magnitude of Q1, Q2 divided by R squared. The value of F is 45. I know that the whole value of this term is going to be 9 10 to the power 9 Q into Q. Magnitude eats away or takes away the minus. So R, sorry, in place of R, it is 0.2 whole square. This magnitude takes away the minus. So in the next term, 45 equals 9 into 10 to the power 9. Q into Q will become Q squared, and whatever kind of charge there may be, since it is magnitude, minus will not come. So Q squared divided by 0.04. When I square this value, I'm going to get 0.04. Now I transpose this and these values to this side. So I get 45 into 0.04 divided by 9 into 10 to the power 9 equals q squared. 9, 5 are 45. So when I multiply these two, I get 0.2 into, when I bring this into numerator, the power become minus equals q squared. I transpose this square into this side, so q equals root over 0.2 into 10 to the power minus 9. I take off this point and take the root. Q equals root 2 into root over 10 to the power minus 10, because when I take off this point, 1 0 will be added here, which means it becomes 10. So Q equals root 2 value is 1.41 into 10 to the power minus 5 Coulomb. So my charges, the magnitude of my charges is 1.141 into 10 to the power minus 5 Coulomb. So this is how I'm going to apply my Coulomb's law. Now test Coulomb's law on this particular question yourself. Then let's do some revision on vectors. So what is a vector? I can define my vector as a quantity that has both magnitude, that means its mathematical value or numerical value, and direction, which we take it to be positive and negative. The negative shows that it is opposite the direction we are taking. Now let's try to do position vector of any point. I take any point A in space. Now there should be a frame of reference where we can find this point in the space. Let's take a frame of reference consists of three axes, x-axis, y-axis, and z-axis. Now the position vector of A will, from the origin J, the distance from the origin to the point A. Position vectors are usually denoted by R. Now it is directed from origin to the point A. So let's say take it RA. Similarly, if I have any point P here, then my position vector B will be from the origin directed towards the B, and it will be denoted by RB vector. Now this is how we denote our position vector of any point in free space. Now we'll try to know position vector between 2 points. I have a distance between A and B. To find this distance vectorially, I can go from A to B and B to A. If I go from A to B, my position vector or distance between A and B vectorially will be given by RAB, where A is my initial point and B is my final point. Similarly, if I'm going from B to A, RBA, then my initial point is B and my final point is A. Position vector or distance, sorry, position vector from A to B. Now, I want to find the position vector from A to B. The position vector from A to B will always be the position vector of final point minus position vector of initial point. So my final point is B, my initial point is A. So RB minus RA. This will give me my position vector from A to B. Similarly, position vector from B to A is going to be given by RBA. So B is my final, sorry, A is my final. So position vector of A minus position vector of B, initial, final. Final minus initial. This is how we are going to use our position vector between 2 points or denote it with this. Now, the magnitude of the above 2 points are always going to be equal because magnitude does not depend on the sign. It depends only on the numerical value. So magnitude of BA will be equal to magnitude of AB. In terms of magnitude, the position vector between 2 points are always going to be equal. In continuation to the vectors, let's try to know what is unit vector, which is denoted by the symbol gap on top of the vector. Now, unit vector means whose magnitude is 1 with direction in it. For example, let's say we have a vector A going from this to this direction, then our unit vector of A will be denoted by this. This is going to be our unit vector of A and is going to be equal to A vector divided by magnitude of A. A vector divided by magnitude of A. Note here, if there is a vector A, then its magnitude can be written as magnitude of vector A, or I can just write A, removing the vector symbol and modulus symbol. Now, let's try to convert Coulomb's law in vector form. Consider two charges here, Q1, Q2. Let's say they are in free space, so I have to bring a frame of reference X, Y, Z. This is my origin. From here to here is my position vector of Q1, and from here to here is my position vector of Q2. Now, the position vector between Q1 and Q2, that is the distance between Q1 and Q2, magnitude of R1 to 2 R1 to 2 is going to be equal to R2 to 1. Let's say both of them are equal to R. Since these two are going to be equal in magnitude, their values, let's say it is equal to R. Now, consider two charges Q1 and Q2 with position vectors R1 and R2 respectively. The magnitude of the distance between Q1 and Q2, that means R12, R21 modulus are going to be equal to R. The magnitude of the distance from Q1 and Q2 are R12 equals R21 equals R. So, as I have said, since these two are charges, a force will be acting on Q1 due to charge Q that is in the direction from Q2 to Q1. Let's denote that force as force acting on 1 due to 2. Alternatively, due to charge Q1, a force will be acting on Q2. Let's say that force is F21. We'll try to find this force using Coulomb's law with direction. Therefore, force acting on Q1 due to Q2 is F acting on 1 due to 2 is going to be equal to 1 by 4 pi epsilon naught. We are not going to take the magnitude here. So Q1, Q2 divided by the distance between the two charges is always in magnitude and it's going to be R. So R squared in the direction of R. Since force is acting from Q2 to Q1, it will be 1, 2, in the direction of 2 to 1. Make this as equation number 1. Similarly, force acting on Q2 due to Q1 is F21 is going to be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R squared in the direction of 2, 1. Make this as equation number 2. Now equation 1 and equation 2 are called as Coulomb's law in vector form. Equation 1 and 2 gives Coulomb's law in vector form. Now, let's take equation number 1 from equation 1 F12 is going to be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square R cap 1 2. Now, if I want to change the direction of 1 2 to 2 1, let's take an example here. We know that RAB is going to be equal to RB minus RA. This is our final. This is our initial. Now, if I want to change this two position, I want to bring A in front, then I'll take minus common, and this will become plus, and this will become minus. So RA minus RB. Now I find that this is going to be RAB is going to be equal to minus RBA. So whenever I change these two positions, a minus comes in the form in front. Similarly, when I change these two positions, a minus should come in the front since every term is multiplication. So therefore, F12 is going to be equal to minus 1 by 4 pi epsilon naught Q1 Q2 divided by R. Since I bring a minus here, I'm going to change the direction of 2 1. Now compare all this term with this equation number 2. So in place of this, I can write F21. So F12 equals minus F21 vector. Now, what does this tells me? This shows the equation of Newton's third law of motion. Newton's third law of motion, which states that to every action there is equal and opposite reaction. To every action there is equal and opposite reaction. So we can say that Coulomb's law also follows Newton's third law. Therefore, Coulomb's law follows. All we can say is consistent with Newton's third law. So this is all about Coulomb's law in vector form. Now, we'll try to bring out some important points on Coulomb's law in vector form. We find that in Coulomb's law in vector form, we find the term Q1, Q2. They are not in magnitude, so we are going to consider the nature or type of the charges, either positive or negative. Now, in the first case, when charges are like in nature, we are going to get Q1, Q2 more than 0. In this case, the nature of force attractive or negative. Nature of force, that means attractive or repulsive. Attractive or repulsive. In this case, the nature of force is repulsive. Let me brief why it is getting more than 0. Let's say we have Q1 here, Q2 here. Let's say this one is positive and this one is positive. In this term, we are going to multiply them. So plus multiplied plus will give me plus, which is more than 0. Similarly, let's say this one is negative and this one is negative, then minus multiplied with minus becomes positive. That means the final result will be a positive value which is more than 0. Similarly, point number 2, when charges are alike, in nature, our Q1, Q2 value will be less than 0. That means we are going to get a negative value which is less than 0. Then the nature of force is attractive. To brief this, let's take the same example. We have Q1 here, we have Q2 here. Let's say Q1 is negative by nature and Q2 is positive by nature. When I multiply these two, I get a negative value here, which is going to be less than 0. Similarly, let's say this one is positive, this one is negative. In this term, I'm going to multiply it. So multiplying it, still I'm going to get a minus, which means the value we are getting is less than 0. So in vector form, if we didn't take the magnitude of the charges, but we take the nature, that means positive and negative sign, and multiply the charges, depending on that, whether we get positive value that is more than 0 or negative value that is less than 0, we are going to get the nature of force which is either repulsive or either attractive. Now, from Coulomb's law in vector form, try to test yourself with these two questions. Let's talk about principle of superposition. This principle applies to all the vector quantities that consist of many or multiple vector quantities in a system. In this case, let's consider a system that consists of different charges, individual charges Q1, Q2, Q3 till Qn. Let's take a charge here Q0. All these individual charges will be given a force to Q0, and I want to find the total charge, total force acting on this Q0. Then, according to principle of superposition, the total force acting on Q0 by the multiple charges, that force will be given by the vector sum of all the individual forces. Vector sum of all the individual forces. So let's write the statement. It states that the total or net force acting on a charge due to multiple charges is given by the vector sum of all the individual force acting on it. I can write mathematically as F total is equal to F1 plus F2 plus Fn. If I want to get the total force acting on a charge, I can plus all the vector forces given by the individual force to get the total. That is the meaning of this principle of superposition. Using principle of superposition, let's try to find the force on a charge due to multiple charges. As shown in the figure, let's take a charge Q0, and there are multiple charges Q1, Q2, and so on till Qn. The position vector from Q1 to Q0 is R01. Similarly, position vector for Q2 to Q0 is R02, and so on. If the individual forces given by the individual charges are F01, showing the direction here, F02 and so on till F0n, then the total force acting on this Q0 F total will be given by principle of superposition. Now let's try to write its expression. To begin with, let me consider a charge Q0 acting upon by multiple charges Q1, Q2, Q3 till Qn, with position vector R01, R02, and so on till R0n. Let's say the individual forces are F1, F01, F02, and so on till F0n. Then, according to principle of superposition, the total force acting on Q0 should be given by F total should be equal to F01 plus F02 plus Q F0n. Now I'll make this equation number 1. I'll apply Coulomb's law of vector to these individual forces and get their values. But from Coulomb's law, F naught 1 will be given by 1 by 4 pi epsilon naught Q naught Q1 divided by R naught 1 square in the direction of R naught 1. Similarly, I can keep on going till F naught n, and I get 1 by 4 pi epsilon naught Q naught Qn divided by R naught n whole square R cap naught n. When I put these values in equation number 1, putting these values in 1, I get F total is equal to, in place of F naught 1, I can write 1 by 4 pi epsilon naught Q naught Q1 by R naught 1 square R cap plus 1 by 4 pi epsilon naught Q naught Q2 divided by R naught 2 square R cap plus dot 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 till F naught n. That means 1 by 4 pi epsilon naught Q naught Qn divided by R naught n square R cap naught n. I can take some common values here. When I take the common, F total equals Q naught is common in all of these. Q naught divided by 4 pi epsilon naught is common in all of these. So 4 pi epsilon naught bracket Q1 by R square naught 1 R naught 1 cap plus Q2 by after taking common, I'm getting this. So this will give us the total force acting on Q naught. I can also write in the form of summation. So F vector total is going to be equal to Q naught 4 pi epsilon naught summation. The number which are changing, I'm going to make it I. So I, the number starts from 1 and ends at n. So it starts from 1 and ends at n. Q I, since this number is changing from 1 to n, divided by R naught is not changing, the second number is changing. So it's going to be I square R cap naught is not changing, the numbers are changing, so I. So this last two equation gives the total force on a charge due to multiple charges. Using principle of superposition and force acting on a charge due to multiple charges, try to solve these two questions.